Good evening, everyone. So welcome to my YouTube channel, Network. So today we are going to see 7th lecture on probability theory. Okay. So in this lecture, we will see total probability theorem. Okay. So let us start today's session now. So what is partition of the sample space? So what is the partition of a sample space? Okay, partition of a sample space. So partition, what is the partition of a sample space? So let S be a sample space. Okay. And B1, B2, E3 up to Bn are subset of S such that Bi intersection Bj is equal to phi for I and j less than equal to n, I not equal to j. Okay. It means what? B1, B2, B3 up to Bn are mutually exclusive events. Okay. Pairwise mutually pairwise pairwise mutually exclusive events. Such that S is equal to mu mu I goes to 1 to n Bi. Okay. Then B1, B2, Bn are called two are called to constitute are called partition of S. Okay. So what is the meaning partition of S? We have a sequence of events P1, B2, Bn. They are pairwise mutually exclusive events and their union is S. For example, tossing a dice, throwing a dice What is the sample space? 1, 2, 3, 4, 5, 6. Okay. Then if I am taking two events, A, so I am taking B1 is equal to 1, 3, 5 and B2 is equal to 2, 4, 6. Then B1 intersection B2 is equal to 5 and S is equal to B1 union B2. So this implies B1, B2 are partition B1 and B2 constitute a partition of the sample space S. So you see this result. Proposition you can see. Okay. Also note one thing. We can write this as a remark. We can write it as a remark. Let S be a sample space okay. Then for any B subset of S, it means for any event B, the subsets B and B complement, or you can say events B and B complement constitutes a partition of S. So why this is true? You see its proof. This is a simple actually. Okay. This is a simple one. Because we know that B complement is 5 and S always can be written as B complement. So this implies B and B complement constitutes a partition of S. Now we are going to prove a theorem. total theorem of total probability. Theorem of total probability. Let S be a sample space and B1, B2, B3 up to Bn constitute a partition of S. Then for any event A, it means what? A is subset of S. We have probability of A is equal to summation I goes to 1 to n. Okay, I goes to n to n. PBI, okay, PBI probability of A related to B. Let's see its proof, how it will follow. Proof. B1, B2 up to Bn constitutes a partition of S. What does it mean? It means this implies Bi intersection Bj is equal to phi for all I and j goes to 1 to n. I is not equal to j. Okay, and S is union of I goes to 1 to n Bi. Okay. So actually, what is the meaning of formally partition? We have this space, sample space as we have this space. So this is my B1. This is my B1. And this is my B2. This is B3. Okay. And this is B4. Okay. And like that is there. And somewhere it is A. Okay. So this is whole S. Okay. Now how we can write A? Because since Bi intersection Bj is equal to phi, so this implies A intersection Bi intersection A intersection Bj is also phi for all I goes to 1 to j to n, I not equal to j, and we can write A is equal to A intersection S, that is equal to then to take intersection this S, that is, but S is equal to this union I goes to 1 to n Bi. So how we can write it? Union I goes to 1 to n B intersection A. Okay. We can write A intersection BJ, okay, where A intersection BI intersection A intersection BJ is equal to phi for all, okay, I and j less than equal to 1, greater than equal to 1 and less than equal to n. I is not equal to j. Okay, I is not equal to 1. So these two events are mutually exclusive. So the pair A intersection B1, A intersection B2 up to A intersection Bn, they form a mutually exclusive event. Okay. Taking probability function both the sides, so this will imply probability of I goes to 1 to n A intersection Bi. Now, this will, because these events are mutually exclusive, thereby mutually exclusive, so this will be distributed. This will convert to summation. P A intersection Bi. So this implies PA is equal to B. Now for any I goes to 1 to n, we have P A related to Bi is equal to P A intersection Bi upon P Gai. Sorry, PBI. PBI. Okay, now solving this. So solving this, what you will get? You will get PBI P A related to P is equal to P. Now from 1 and 2, we get P A is equal to summation I goes to 1 to n PBI PA related to B. So this is the formula. Okay. Now we will see some example on it. Example. Okay. In a certain assembly plant, three machines, three machines, B1, B2, and B3, B1, B2, B3 make 30%, 45%, and 25% respectively of the products. Okay. It is known from past experience that 2%, 3%, and 2% of products made by each machine respectively are defective. Okay. Are defective. Now suppose that a finished product is randomly selected. Okay. What is the probability that it is defective? Okay. Let's see its solution. So we'll consider the event. Let A is the event, the product is defective. Okay. B1 is the event, the product is made by machine B1. B2, the product is made by machine B2. B3 is the product made by machine B2. So what is the probability now? Because the assembly plant has only 3 machines, so B1, B2, B3. 4 partition of assembly plant, because these machines are distinct, they are mutually exclusive. And this 4 partition, because their union is whole plant, it means sample space. Okay. So applying the theorem of total probability. We get what we get. PA is equal to PB1, PA relative to B1 plus PB2, PA relative to B2 plus PB3, PA relative to B3. Okay. Now, what is PV1? Now, PV1 is because 100% product is made in assembly. So, B1 machine makes 30%. 30 upon 100, that is 0.3. So, what is PB2? 45 upon 100 upon 100. So, this is 0.45. And what is PB3? 25% is made by B3. So, this is 0.25. Okay. Now, what is this? PA relative to B1. B1 event is happened, and then we are calculating probability of A1. But A1 event is the product defective. So B1 event is done. So once B1 event is done, B1 machines make 2% of defective cases. It means whole 2% will be there. Okay, and we are calculating with respect to B1. And B1 machine makes 2% defective of itself. So what is this? This is 2 upon 100. We are calculating this event as taking B1 as a sample space. But the 2% is defective with respect to B1. So it is 2 upon 100, 0.02. Okay. Similarly, what is this? P A relative to B2. Similarly, this is 3 upon 100, 0.03. And what is P A relative to B3? This is 2 upon 100. This is 0.04. Therefore, the required probability is therefore PA is equal to PB1, P relative to A B1 plus PB2, P A relative to B2 plus PB3, P A relative to B3. So what is this? This is 0.03. This is 0.3. This is 0.3 and multiply by 0.02. This is 0.45 multiply by 0.02 and this is 0.25 multiply by 0.02. So this is 0.006 and this is 0. Okay. This is 0. This is 0.0135. Okay. And this is 0.0050. Okay. So what is this total? This is 0.0135. So you can add here 1 0 here. So what is this? This is 0. This is 5. 4 here is there. Okay. Now, so let me add this again. So this is 0 is here, and this is, sorry, 5 is here. 5 is there. 5 is here, and 6, 9, 4, 1 carry there will be, okay, 2, 0, 1, 2, okay. So this is the answer. So today's lecture up to this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you in next lecture.